Hello, my name is M.Mousavi, and this presentation is about my research titled Resilient Lightweight Structural Systems for Microgravity Environment. This research was done under supervision of Dr. Elise Newman and Dr. Michael Carlos and was supported by the DBE department at Clemson University. First of all, I'll walk you through the introduction, literature review, research design and methods, implication for practice, conclusion, and references. In recent years, orbital launches have significantly increased, from around 80 per year in 2013 to over 193 by 2023. Driven not only by government agencies, but also private companies like SpaceX and Blue Origin. This rapid expansion shows that the need for efficient, lightweight, and adaptable structures for space environments. Extreme space environments requires a structure that are not only lightweight, but also adaptable and resilient. However, current structural design approaches often overlook natural biology models and rule-based generative design systems, which have the potential to improve adaptability and performance in microgravity environments. This study combines two powerful ideas, biomimicry and shape grammar, to develop a structural system suited for space. Biomimicry offers inspiration from nature, while shape grammar allows for systematic rule-based design generation, which can address the challenges of building in microgravity conditions. Although biomimicry and shape grammar have been individually explored in architectural design, their combination for a space application, specifically under microgravity conditions, is under research. That's the gap my study addresses. My research explores three main different questions. The first one is how can biomimicry guide the design of the lightweight space systems? The second one is how can shape grammar translate natural forms into modular adaptable designs? And third one, how these systems perform under microgravity conditions. The objectives are to conduct a geometric analysis of biological organisms, generate a modular system using shape grammar, and simulate the test their performance under microgravity to assess their feasibility. The research literature map integrates interconnected themes of the research, including biomimicry, structure, computational design, and simulation. Each theme is divided into two or three subcategories. For example, this slide shows a primary and secondary sources and their connections. The research is divided into three different phases. The first phase is a geometrical analysis of radiolaria and morphogenesis. The second phase is a generative design of the space systems and their modular configuration by using shape grammar. And the third phase is testing and simulation of generated designs under microgravity conditions. Radiolaria are marine microorganisms known for their mineral skeletons. They naturally optimize geometries inspired by the abstraction of the forms into Platonic solids, mainly tetrahedrons and octahedrons, which provide structural stability and modularity. Platonic solids, due to their symmetry and structural integration, are ideal building blocks. They are highly symmetrical, stable, and ideal for modular structures. The result of the first stage is a generating two fundamental shapes. The one is tetrahedron, and the second one is an octahedron as an initial shapes. The second stage, I've implemented the foundation of the space structures and shape grammar theory. The shape grammar is a rule-based design system used for analyzing existing design and generating a new ones. It works by applying set of rules such as rotation, reflections, scaling, or translation of basic shapes. These rules guide how shapes are combined or modified. The shape grammar consists of four elements. The first one is initial shapes, second is spatial relations, and third is a rule and designs. For instance, this slide shows all possible designs from shape grammar were generated based on specific rules to determine the number of possible designs. The outcome of the second stage is the generation of the diverse design by applying shape grammar rules to fundamental polyhedral shapes. In the third phase, I will simulate this system to test their structural performance in microgravity using a parametric modeling environment, for example, Rhino and Grasshopper, combined with the structural analysis plugin like Karamba 3D. The key goals include optimizing load distribution, minimizing material usage, and modular configuration for space missions. By genetic algorithm to identify high-performing configurations based on applications features. As a final stage, we expected that this space system can be implemented for designing various applications like solar arrays, lunar or Martian habitats, and antenna system. In conclusion, my research proposes integration of biomimicry and shape grammar to develop modular space systems. By abstracting natural geometries and systemizing their transformation, we can generate lightweight structures optimized for space applications. This slide shows the research follows in three-phase timelines. First on is analysis of biological models, generation of modular system using shape grammar, and simulation and testing under microgravity environment. Each stages builds directly upon the last, leading to the comprehensive design and evaluation process. The research is based on the wide range of sources across biology, structural design, and computational methods. Thank you for your time and attention. I look forward to your feedback and questions. Thank you.